Hello everyone, greetings. Today we're going to go over the long-awaited Dirac equation. And this is a very interesting topic that has a very nice rich history behind it. And I'm very excited to show you guys how to solve the Dirac equation for a free field. So let's begin. So first let's give a brief overview of the Dirac equation and what's in this video. So to start with, we're going to first define the Dirac ansatz. And from there, we will solve the Dirac equation with this ansatz. Then, we will comment on the negative energy solution to the Dirac equation, and then talk about why it's relevant. Why does negative energy matter? And then, lastly, we will talk about solutions to kind of fix this negative energy conundrum that comes from the Dirac equation. Now, there are a bit of prerequisites to this video, like all videos of mine. To start with, you guys need to know how to derive the Dirac equation. It's a very big part of understanding why the Dirac bispinor is a 4x1 matrix and a spinor, and then talk about how you derive the Dirac equation in my space-time algebra video. Now, in hindsight, I probably should revise that video, since I didn't give the Clifford algebra, which is formed by gamma matrices, and the Clifford product at the end of the video. I didn't give like the exact one, so probably will remake that video. But for now, it's still a good video to watch, since the relevant part is driving the Dirac equation, and I did that part correctly. So yeah, watch that video if you don't know how to derive the Dirac equation. There's some pretty nice insights in it. Then, watch my Introduction to Spinners 1 video. If you don't know what a spinner is, like, I'm gonna say spin like a billion times this video. Like, be my guest to like count how many times we'll say spinner. So know what spinners are, and then watch my video on Dirac spinners. Because the Dirac spinner is the solution to the Dirac equation. And so yeah, watch that video if you like. Yeah, just watch the video. And then the wall spinners are relevant since you stack on the wall spinners to form the Dirac spinner. And this is like the big crucial part. I can't emphasize this enough. Watch my solution to the Klein-Gordon equation video if you don't know how to solve the Klein-Gordon equation, because that's like very relevant for this video, and you'll see why shortly. And then if you don't know how to solve the Schrödinger equation, watch this video, how to solve it for a free particle. Though I'd assume that if you're watching a video on how to solve the Dirac equation, you'd watch a video on how to solve know how to solve the Schrödinger equation for a free particle. I hope you guys can. So yeah, but like if you already know these things, you don't have to watch the videos, like of course. But if you don't know these concepts, here are the videos to watch. And if you guys like know the things already, well, that's even better. Now, this is the part where everyone hates we have to get a notation done. So, in this video, I'll be using a bit of a different notation, well, very big difference of notation, compared to the standard text on QFT. Now, what annoys me is that most textbooks on quantum field theory, they use indices for vectors, and they use arrows for vector indices. Sorry, I wrote that incorrectly. They use indices for vectors, and then they use arrows above letters for vector components. Now, the annoying part with this is that in linear algebra, you use vector indices for the components of a vector, and then you use the arrow above the letter for the vector. And for some reason, QFT textbooks like flip this notation around completely, and it's like really confusing for someone that has a solid background in linear algebra. So in this video, I'll be helping the little guy out, and I'll be using the linear algebra notation for everything here, because it's just much more easier to understand. Like, I don't know why they do that. In my opinion, it's a stupid notation that they use, to put it bluntly. So yeah, we'll be using the linear algebra notation since like a lot of the concepts here are really motivated by linear algebra. So here's the notation here. This area above the letter represents the K4 vector. I have the four components here. K mu is a mu component of this K vector. K dot with K. K vector dot with K vector is K mu, that's just the inner product, which equals this. We can also rewrite K, the K vector, as K naught in K without anything on it, where K naught relates to energy, and then K is defined as like the lower three components, just combined into like one letter. That's the 3 vector. This one relates to momentum, and this relates to the energy. This shouldn't be anything new here. Again, if you have the prerequisites, this should just be a brief review. And then probably like one of the most important things here, we have the energy, Einstein energy momentum relation at the bottom here. This is just like the relation in disguise, K mu equals m squared. And you can see a justification for that right over here. So with all that stated, let's solve the Dirac equation. So, how do we solve the Dirac equation? Well, we start by writing down the Dirac equation, right? And again, you should know what every component here means. If you don't know what the components mean, watch your previous videos. But yeah, nothing odd should be here, because you know what each part means. So, what we can do here is we can kind of simplify this equation a bit. So, let's define some operator called the Dirac operator. And this acts on psi and it outputs 0. And we're going to define this operator as I gamma mu partial mu minus m. So all we're doing here is we're just rewriting this entire term as d hat to make our calculation more compact. Okay, so let's just for fun, multiply both sides by the Hertzian conjugate of this Dirac operator. And of course, anything times 0 is 0. Now, what's the Hertzian conjugate? Well, the Hertzian conjugate of any operator, you just take, you just put a negative sign next to the complex part. So what we have here is a new equation. And this Dirac bispinner that solves this Dirac equation will also solve this equation, since all we did here was just multiply both sides by the Dirac Hertzian conjugate. So let's actually find out what this term evaluates to. So we have minus I partial mu minus m times I partial mu minus m psi equals 0. So you just have to distribute these terms. First, then outers, inners, and then lasts. All of this times psi gives us 0. Okay, so let's simplify here. So what can we do? Well, these cross cancel out. We get an m squared here. These cancel out. So we have positive I gamma mu partial mu m. Here we have minus m I gamma u partial nu. So these terms will cancel out. These cancel out to minus 1. These cancel out. What we have now is partial mu, or so let me just rewrite that. We have partial mu, gamma mu, partial mu, gamma nu, plus m squared times psi equals 0. And if you can recall from our space and algebra video, this is the definition of partial mu. And you can justify this yourself by just taking the Dirac anti-commutator of the gamma matrices. So you might notice that this is exactly the Klein-Gordon equation, right? And the Dirac bispinner, what solves the Dirac equation, is also going to solve this Klein-Gordon equation. Again, all we did here was use multiply both sides by measuring conjugate. We obtained this relation over here. We expanded this, and we found out that it gives us the Klein-Gordon equation as an output. So the Dirac bispinner will solve the Klein-Gordon equation. And if you remember from my Klein-Gordon equation solution video, the most general solution to the Klein-Gordon equation is a superposition of plane waves over K. So here is our general solution to the Klein-Gordon equation that I derived in my video titled that. So we notice immediately here that it's just a superposition of these plane waves, e to the I k mu x mu and e to minus I k mu x mu. I'm not sure this is the exact word for word general solution. I have to double check, but it looks something like this. And the point here is that it's basically just taking it's literally taking the linear combination of these plane waves. Now, this is the most general solution to the Klein-Gordon equation. So if the Dirac bispinner is going to solve the Klein-Gordon equation, and the most general solution to the Klein-Gordon equation is written in a plane wave basis, that means that the Dirac bispinner will have a plane wave basis, since again the most general solution will have plane waves. So this motivates us to take the ansatz, where psi equals he to the minus ik mu x mu, and psi equals he to the plus I k mu x mu. And we use this as the ansatz for the Dirac equation. And here h is defined as the two Weil spinners. So again, these are the two Weil spinners, and we're using Weil spinners here since remember that the Dirac equation is going to be a 4-component spinner. So we're going to have the Weil spinners here. So that's why we have that. And then you have the plane wave basis, since it has to have that, since the most general form will have a plane wave basis. So using this ansatz, we can solve the Dirac equation pretty easily. So let's just write down the Dirac equation once more. Okay. So what we do now is let's plug in one of our ansatz in this equation. What we do now is we just distribute this term in. Now we take we take the derivative of this, because it's minus ik mu times e to the minus ik mu x mu minus mh e to the minus ik mu x mu. That's 0. These i's cross cancel. Then I have partial mu h, k mu e to the minus ik mu x mu minus mh e to the minus ik mu x mu equals 0 minus mh e to the minus ik mu x mu 0. So all we're doing here, just taking a derivative, nothing too fancy here. So now we've arrived at this expression over here. And now it comes to where we are going to impose two conditions on our spinner. 1, we impose the mass on shell condition. This isn't any loss of generality here, since real particles must obey this relation. So when we are imposing this condition, we're basically saying we want our solutions to represent real physical particles. So no loss of generality here. 2. Now we are going to work in a co-moving rest frame. So this just means that we are attaching our frame of reference to a system, and that system is in the rest frame, so it's going to measure its own momentum as 0. So this is a loss of generality here, since now instead of working in a general frame of reference, we are working in the rest frame of reference, which is only one particular frame of reference. And so our solutions are going to be in the rest frame. But that's not a big problem, since in the end, you can just boost our solution, give it a Lorentz boost, to boost it to the general frame of reference. So this does give us a bit of a loss of generality, but we can just Lorentz boost it at the end. And the Lorentz boost will actually be done in another video for sake of time. So this k equals 0. Again, this is the k3 vector. So we are basically saying here that k1 equals k2 equals k3 is 0. That's the rest frame condition. So using these two conditions, we can actually simplify this part a ton. Like, really a ton. So, first of all, e to the minus I k mu x mu. That's e to the minus I times k naught x naught minus k1 x1 minus k2 x2 minus k3 x3. And since these are 0, these will go to 0. I have e to the minus I k naught x naught. Now remember, k mu equals m squared, right? But that's just k naught minus k1 minus k2 minus k3. But these are all 0 since we are working in the rest frame. So this equals m squared, right? So this implies that k naught equals m. So this simplifies even more to e to the minus I m, and x naught is of course defined as t, time. Alright, and we can also simplify this term as well. So you have I keep calling it partial, gamma mu, hk mu minus mh. This simplifies to gamma naught hk naught minus mh. Again, because when we expand this, the other k terms are 0, and they all go to 0. So this simplifies down to y naught hk naught minus mh. Now you can remember that k naught is actually equal to m, so this becomes m. And finally, what we have here, after doing all these simplifications, is that we have y naught hm minus mh e to the minus imt equals 0. Of course, implying that y naught hm minus mh equals 0. Cancel both sides by m. You have the gamma naught h minus h equals 0. Alright. That's what we have here. Now, note, let's just rewrite that down again for just simple reference of the viewer. So, y naught, that's 0, and data matrix 0. That's 0, 1, 1, 0. And then this is chi epsilon, and this is 0. Okay, so a bit of notation stuff here. So, first of all, this gamma matrix is being written in the what we call the Chiral basis. Now, using a different basis will change what our matrix looks like. In this basis, we are using the Chiral basis since that's easier to solve the Dirac equation with. There are other bases like the marijuana basis. I call it the marijuana basis. It's not pronounced that way, but I always my brain always slips up. It's like the Majorana basis. There's also the mass basis, also called the Dirac basis. But in this video, we're using the Chiral basis for our gamma matrices. Now, also, our gamma matrices are really for, oops, that just happened. Our gamma matrices are really 4x4 matrices here, right? But what we're doing here is instead of like having to deal with 4x4 matrices, instead of writing it as a 2x2 matrix, and instead of make each entry represent a matrix of their own, just like how we take the Dirac bispinner, give it 2 components, and make each component have their own components, right? So here 0 is defined as the 0 matrix, and 1 is defined as the identity matrix. Alrighty? So what we do now, so when you multiply this out, we have 0, you have epsilon here, chi, it's just making multiplication here, minus chi epsilon equals 0. And this now implies that epsilon equals chi. Since for this to be 0, epsilon would have to be equal to chi. So now let's remember that our ansatz is h e to minus I k mu x mu. And that's just chi epsilon e to minus I k mu x mu, since h is defined as chi epsilon, that matrix. And remember that chi, if we just found that chi was equal to epsilon, so you can just rewrite this as chi e to, minus imt. And yeah, that's our answer. That's our solution. Now, chi, we don't have any, like, limits placed on chi. Chi can be any number we want. But we can choose a linear independent basis, since it can form any solution to the Dirac equation. So let's choose chi to be 1, 0. We can also choose chi to be 0, 1. So now we have that the Dirac bispinner is 1, 0, 1, 0, e to minus imt, and it also is 0, 1, 0, 1, e to minus imt. So again, all we're doing here is we're choosing chi, like values for chi, to form a linear independent basis. And from this linear independent basis, we can take superpositions of these two to form more solutions to the Dirac equation. Because again, we can choose any value for chi. We just conveniently choose it to be these two values to form more values. Alright, so that's like only half of these solutions. Just remember, our other ansatz, we had another ansatz that was psi equals h e to the I, posited by k mu x mu. But before we get to that, let's talk about the energies of these two solutions. Let's just number it conveniently 1 and 2. So even though our Schrödinger equation is antimatter operator acts on psi, gives us energy times psi. In the weird land of Einstein notation, the Einstein operator is just, what is it again? I partial naught psi, and that equals E psi. So let's actually calculate the energy of, well, the electron that has, that's in, blah. Let's calculate the energy of this Dirac bispinner. So all we do here is we just plug in e to minus imt, like this e times e to minus imt. So this derivative is just minus im times e to minus imt equals e to minus imt. This cancels out. We have m e to minus imt equals e to minus imt. So e equals m. This is expected. Oops, you guys couldn't see that. So this is expected. Makes perfect sense. E equals m. So this means that these two fields correspond to a particle with an energy of E equals m. So what for our other ansatz? Psi equals h e to the I k mu x mu. So again, for this other ansatz, we just do the exact same thing, just using a different, slightly different value. So I'm going to go a bit faster since it's the exact same thing, but with a positive exponential. So yeah, let's do that on a new piece of paper. So our ansatz here, we're just going to kind of speed through this. distributing the term here. Okay, so now what we do again, just take the derivative. Oh my gosh, bruh. Okay, oops. Made a mistake. I forgot. We're dealing with e to the plus I k mu x mu, not e to the minus I k mu x mu. Sorry about that, but it's fine. This is just h times I k mu, not minus I k mu, since it's positive, right? So I k mu e to the I k mu x mu minus mh e to the I k mu x mu equals 0. These cancel out to be minus 1. Factor and again we impose the two relations, mass on Chiral condition, so no vertical particles, and the rest frame condition. And this gives us minus gamma naught h, is that a k? Circle my writings here. K naught minus mh IMT equals 0. And this is just an m. These m's will cancel out. We have minus this h, still an h here, equals 0. So we have minus this, oops, should be a 1. Here, let me just rewrite it again. So you have minus 0, 1, 1, 0 times chi epsilon minus chi epsilon equals 0. Just distribute the negative 1 constant scalar in here. Distribute, just do this matrix multiplication here. Gives us, this is 0, you have minus epsilon minus chi. Let's get minus chi here, right? Minus chi epsilon equals 0. This implies that minus epsilon minus chi equals 0, where the minus epsilon equals chi, where the chi equals minus epsilon. So our ansatz originally was h e to the I k mu x mu. Just found it because that psi is just, again, chi epsilon e to the IMT. Epsilon, well, chi is just minus epsilon, or epsilon, excuse me, epsilon is minus chi. So that psi is chi minus chi e to the IMT. Again, we can just form a linear independent basis here and choose chi to be 1, 0 and 0, 1 respectively. We have that psi is 1, 0 minus 1, 0 because it's minus chi now, e to the IMT. And psi can also be 0, 1, 0 minus 1, e to the IMT. Nice. So those are our two other Dirac solutions. What we can do now, so let's just write all of our solutions that we have. So we have 1, 0, 1, 0, e to the minus IMT. We have 0, 1, 0, 1, e to the minus IMT. We have 1, 0, minus 1, 0, e to the IMT. Here we have 0, 1, 0, minus 1, e to the IMT. But remember, we actually found out, so let's just write it down below here. We found out that e equals m for these two terms here, right? Take e to the minus I, oh, e equals m, right? So yeah, e to the minus IAT. Psi 2, 0, 1, 0, 1, e to the minus IET. What about these terms? What are the energies for these terms? Well, again, Schrödinger equation time. So just plug in h e to, oh, we don't actually need the h here. E to the IMT, right? E IMT all we're doing, sorry if it looks like I'm just like mumbling along, just a straightforward derivative here. So this is just going to be im e to the imt, e times e to the imt, minus m e to the imt equals e to the imt. So e equals what? Minus m. Do you do anything wrong here? E equals minus m. What? Negative energy? No, we do not do anything wrong here. This is a fundamental historical notice of the Dirac equation. We get negative energies. So psi 3 is 1, 0, minus 1, 0, e to the, well, this is it was e to the imt, but e equals minus m, so m is minus e. And then psi 4 is 0, 1, 0, minus 1, e to minus I, et. So here we have positive energy solutions. Here we have negative energy solutions. How about that? So it's a famous solution of the Dirac equation. It gives us negative energy solutions. So what is that all about? So negative energy solutions. How many types again am I going to say that? So this is actually a big problem with the Dirac equation. I might be wondering, well, why? Why is it a big problem with the Dirac equation? And this is the answer. So, in elementary QM, so let me just like write normal. In normal QM, we have energy eigenvalues. So here's the zero, like vacuum state, because I guess you'd call it. E naught equals 0. Here you'd have E1, here you'd have E2. Yeah, that's just it. Yeah. And then you have E3 and stuff. So you have a particle that's, say, in the E3 state. And the particle is more likely to be found in the lower energy states. For reasons that, like, you learn in any intro to QM class. So the particle is more likely to be found in lower energy states. So the particle would just, if it's in E3, it would just drop down to, like, say, E2, then to E1, then to E naught. Sorry, not E naught. It's going to stay at E1. It's not at E naught because particles having 0 energy means that the particle doesn't exist in normal QM. So yeah, it would just chill at E1, not at E naught. It's not going to drop down there. So yeah, particles at E4 is going to drop down to the bound state. Now, if we have multiple particles, it's a bit different since we have the Pauli exclusion principle. But just ignoring that, usually, yeah, the particle will just drop down to the ground energy, E1. But now in the Dirac picture, things are a bit different. Now, again, we have E naught equals 0, E1, to E3, and up to infinity. But now we also have negative energy. So E1, that's just m squared. So on. Sorry, not m squared, m minus m. Close rush frame, right? If E minus 2, E minus 3, and so on. Again, remember, the particle is much more likely to be found in the lower energy state. So the particle might be cruising at E2. It's going to drop to like E1, right? It's more likely to be in a lower energy state. Now here, it would just go down to E1 and it stays there. It's done. There's nothing lower than that. We have a ground energy. But here, no longer true. There is an energy smaller than E1, like E minus 1. So the particle will drop down to E minus 1, that state. It's going to release a photon, right? And the particle is going to keep going down, right? Because a particle is more likely to be found, or it's more likely to be measured in a state with a lower energy. But there is no cutoff on lower energies. The particle can just keep getting a lower and lower energies. The particle is in this rabbit hole where it keeps falling down, and it keeps getting into a lower and lower energy states. And the particle can just keep emitting photons, right? Like, and the particle just keeps emitting photons, and it keeps emitting like an infinite number of these photons, in fact. And we don't measure electrons like just emitting an infinite amount of light, right? So something is clearly wrong here. The particle just keeps falling down, keeps emitting photons. Like it goes from, say, E equals M to, EM to E naught. Photon of energy, E of energy M, goes from this state to this state. Photon of energy 2M. So yeah, it just keeps releasing energy, and we don't observe that. It's a problem. So we're kind of stuck. Now, Dirac proposed a solution to this problem called the Dirac sea. So he was like, okay, let's solve this thing. So we have E naught, let's just write it again, E naught minus 1. Then you have the upper energies, right? So Dirac goes, okay, so we don't want the particle to just keep releasing energy ad infinitum. So he envisioned there being an infinite number of electrons all throughout space occupying these negative energy states. So you have an electron here, E minus 4 electron there, and so on. So you have an infinite number of electrons occupying this negative energy state. And this solves the problem. Because, say you have a particle at E1, well, it can't drop down to E minus 1 because there's already an electron there. Remember, electrons are masters at social distancing. The Pauli exclusion principle prevents the electron from going to that state because there's already an electron there. It's like an infinite hotel, right? And all the rooms are occupied. The electron doesn't have any room to go to that negative state. This prevents the electron from emitting an infinite number of photons because all these electrons, they're just chilling there, filling all the negative energy states. So this was Dirac's solution to this picture, but it's kind of queer because in this solution, not really a solution, cough cough, we have an infinite number of electrons at every point in space. Because remember, this field exists everywhere, right? So you're going to have an infinite number of negative energy electrons at every point in space. And you have an infinite charge density. Now, of course, you can counteract this with a positive, an infinite positive charge density, so counteract the infinite negative charge density. But it becomes really wild here. And it's kind of like in flat Earth, the flat Earth hypothesis. You say, okay, the Earth is flat. Again, I'm no way saying that Dirac is a flat earther. I'm not saying that he's like a flat earther. This is just an analogy here. But it's like how in flat Earth, you say, okay, the Earth is flat, and you get a lot of problems when you say that the Earth is flat. So a flat earther would say, okay, well, the sun is very small, and it's orbiting the Earth, and the light acts in this way, and the stars all move in a different way. The flat Earth has to make more and more ad hoc assumptions to make their model fit observations. And these assumptions aren't justified, and they seem quite arbitrary as well. And that's kind of like what's happening in this picture. Again, Dirac's not a flat earther. This isn't like any flat Earth conspiracy thing. No, just an analogy. But Dirac said, okay, we have this Dirac sea, that's what it's called, this picture of an infinite number of infinite number of charge at every point in space. To fix it, you have to have a counter charge at every point in space. It's just a big mess. It's not very nice. It's not beautiful at all. In this picture, this idea was heavily criticized, actually, in Dirac's time. Most notably by Werner Heisenberg. In fact, Heisenberg said that this was the most embarrassing, most stupid idea, in modern quantum physics. It was that poorly received by Dirac's peers, because you have this model where there's an infinite number of electrons and there's an infinite number of counter electrons. It's really ugly. But Dirac's model kind of worked. Let's actually explore it more. So Dirac was like, okay, these are all occupied. But what happens if a photon hits one of these electrons? Say a photon hits the electron at this state. So this is minus m. Photon with energy 2m hits the electron, okay? And the electron just moves up to the E1 state. Now there's a hole in the E-1 state. No electrons here, right? So this guy that's already here has to get kicked out. Has to go down to the E-1 state. Simple, right? Makes sense so far. So again, you have a photon here. The photon makes this negative energy electron get positive energy. This guy has to create a photon, go downwards. Now this it's kind of like this gap, this hole in the Dirac sea acts like a particle itself, right? Like the Dirac sea is unobservable. You have an infinite number of negative charge with an infinite number of positive charge that just so happen to counteract each other. But this hole in the sea would be observable, right? I mean, this will act like a particle. It acts like a positive charge electron. So when there's a hole in the field, right? Like when you, say you hit a photon, right? Pushes an electron to the positive energy spectra. Well, it's sort of like the photon is creating an electron and some anti-electron. Let's just call it an anti-electron pair. So when the photon hits this electron, it goes here. There's a hole, right? This hole acts like a particle, and then I have that particle over here. So it's like the photon comes in and creates an electron anti-electron pair. And when this electron falls to this gap, it releases a photon. So it's sort of like how it's like this hole in this electron kind of annihilate and release a photon as a response. So holes, gaps in the electron field, they act like particles themselves. So again, I'll just give a nice picture here. Holes in the field will act like particles. If a hole moves up, that just corresponds to particles moving downwards. So when this guy goes downwards, you have a hole here now. So it's like a hole moved upwards. When a hole meets an electron, they annihilate. A photon's released, and the electron takes up its place, and so on. So Dirac noticed this, and he said, "Okay, guys, this hole in this infinite Dirac sea is a particle," and he called it an anti-electron. He said, "Okay, we can observe this in an experiment, since there is a asymmetry sort of in this Dirac sea. We can detect that." Now, Dirac originally actually thought that this hole was a proton, but then good old Oppenheimer, the bomb guy, pointed out to Dirac that, well, if the hole is a positively charged proton, then you deal with protons and electrons annihilating, releasing photons, and we don't observe that. So Dirac had to reject that theory and say, okay, it's a holding particle in of itself. Now, this Dirac sea picture, there are still many problems with it. It's not correct. Again, you have the problem of ad hoc assumptions to make your model fit reality. And there are more problems to it, like the behaviors of this hole, how you detect this hole, whether or not it's an accurate model of reality. So the Dirac model was ultimately rejected. Now what happens next is that Feynman comes along. And Feynman's like, okay, I think I have a solution to your infinite photon energy problem. So Dirac goes, okay. How about this? Instead of taking the energy to be negative, what if instead you treated the energy as positive? So your energy is positive, but it's just time that's negative. So the time absorbed is a negative factor, and you call that time now. And time, this new time, that's negative. And this sort of fixes your problem, because you no longer have negative energies here. Because again, you have this minus sign. Originally here, this is a negative value, but I'm just saying this with the positive, and instead absorb this minus sign with the t, and this I call t the negative amount. So that sort of works out here. And it's pretty weird. Particles going backwards in time. What does that really mean? But it kind of fixed the picture. In fact, this is actually reflected in Feynman diagrams. So consider scattering with an electron and an anti-electron. So you have an electron here, anti-electron. The electron moves forward in time. This one moves backwards in time. And yeah. Oh, this should be this way, sorry. So that was Feynman's kind of fix to it. Just treat the particle as this minus IET. Well, E isn't negative, it's time that's negative. And treat E to be positive, particles just going backwards in time. Kind of fix things. But now you have particles going backwards in time. So that has some really nice philosophical implications. I recommend checking it out. But yeah, this was Feynman's sort of fixed the problem. Now, of course, whether or not you really believe that they're going backwards in time, that's up to you. But yeah, this was his fix to it. Now, in quantum field theory, the problem vanishes entirely. Because what happens is that you quantize your field. So the actual answer isn't backwards particle, it isn't any Dirac C. Instead, the answer is quantizing your field. When we quantize the electron spinor field by defining the commutation relations between the field and the momentum field conjugate density, what is this called? You define the commutation relations, and your field is quantized. When your field is quantized, it's not written in terms of like creation operations and stuff, and the problem of negative energies go away. This is only a result of your field not being quantized. And again, we'll actually go into that in depth when we actually talk about field quantization, second quantization, as it's usually called. But that's that's a future video, and you'll see why it solves the problem. And yeah, like some people prefer people teaching QFT, just like teach second quantization right off the bat. But that's a mistake. It's a bad approach. Like even I don't fully understand second quantization yet, but it's much easier to understand once we have the classical field theory first, and then we just copy and paste it and quantize it. So what we're doing right now, technically speaking, it's called relativistic quantum mechanics. And what we do, all we do is we just define some commutation relations, and we just quantize the field, and things carry over, and our infinite energy regress problem kind of thing goes away. So if you didn't understand that, completely fine. We will cover that in a future video. But yeah, and also in quantum field theory, we still kind of treat the field as going backwards in time, sort of. That can still be done there. So it is a perfectly consistent model, actually. Whether or not like you take that as math trick or literal, up to you. You could debate about it, but yeah. So yeah, that is the Dirac equation solutions. And yeah, I hope you guys enjoyed this video, and have an amazing day. See you guys next time, as always. Bye.